Hi everyone. So in this video today, we're going to be talking about linear and angular speed. So they are related to each other. And first, let's just talk about what each one of those are. So specifically, we're talking about here when something is rotating, like a wheel or a disc or a saw, something circular is rotating. So the angular speed, that's going to be in terms of like, let's say revolutions per minute, or sometimes that's written as RPM. That'd be revolutions per minute, or it could be radians per hour, right? Because radians is a measure of angle in a circle. It could be degrees per minute or second. Okay, so angular speed is just basically how many rotations something is doing in a certain amount of time. Okay, so the variable that we usually use to represent angular speed is called omega, and it's kind of like a little lowercase w, just a little more curly. So that is the angular speed, okay? How many revolutions per minute? The linear speed is usually represented by v, velocity. So the linear speed, and again, we're talking about rotations here. So this would be like if I were to choose a spot on the outside of the circle, that's how much ground that thing is covering in a certain amount of time. So another way to say that would be it's the speed at which a point on the edge of the circle travels around, okay? So if this were a bicycle tire, it would be how much linear distance that point right there would actually be covering as the wheel spun around, okay? So we're gonna actually go ahead and learn how to calculate both of these. One thing that I want to point out here is that these two things are related to each other. And the way that they are related is that the linear speed is equal to the angular speed times the radius of the circle. Now, in order to use this relationship, the angular speed needs to be in the form of radians per second, or actually it doesn't necessarily have to be per second, but just per time. So it could be seconds or minutes or hours, but we want to have radians per time before we just times it by the radius to get the linear speed. Okay, so let's go ahead and just look at a couple of examples. So our example one here, so this is on the worksheet that you have for today. The first four are going to be examples that we do together in this video, and then the rest of the worksheet will be your homework. So if you guys haven't gotten that yet, let's take a second and get that passed out, and then you can follow along here. All right, so example one, the second hand of a clock is 10.2 centimeters long. So the second hand in a clock, that's the one that counts seconds, right? So it's the long one. So basically it's the radius of the circle is 10.2 centimeters, okay? Find the linear speed of the tip of the second hand in centimeters per second. Okay, so we are looking to find linear speed. In order to do that, we want to take the angular speed and multiply it by the radius. But remember, we need our angular speed to be in this radians per amount of time. That's what we want the units to be before we start. So I know that angular speed is just equal to however many revolutions in however much time. So think about the second hand on a clock. We know that it goes all the way around, since this is a clock and it's counting seconds, it goes all the way around in 60 seconds. So the angular speed is one revolution every 60 seconds, right? It gets around in 1 second. In 60 seconds, but we need to change this to radians. And remember that in radians, one complete revolution is 2 pi radians. So in order to get this in radians per per time slot, which we have here per seconds, we're actually going to times this by 2 pi radians per 1 revolution. So the angle changes by 2 pi, if we're in radians, every 1 revolution. So the revolutions are going to cancel here, and we're just going to be left with 2 pi divided by 60. So when I put that in my calculator, I got about 0.48 radians per second. Okay, and then once we have that angular speed in radians per time, now we can go ahead and we can find the linear speed, which, remember, the linear speed is related to the angular speed. We just have to multiply the angular speed by the radius. So our radius is 10.2 centimeters. So we're just going to take that 0.48. That's radians per second, right? And we're going to times that by 10.2 centimeters, okay? So the radians, oftentimes when we have radians somewhere, we don't really write it, but we're just going to go ahead and multiply these together, and this is going to give us centimeters per second. So if I multiply 10.2 by 0.48, that gives me about 4.97, and that's centimeters per second, which is the units we want our answer in. So here is the linear speed, okay? In order to get the linear speed, we first had to calculate the angular speed, right, in radians per second. So let's go ahead and look at number 2. So we have an 18-inch diameter tire on a car. So here's the tire here. It looks like the diameter is 18 inches, which means the radius is going to be 9 inches. It makes 9.3 revolutions per second. So it's turning around 9.3 times every second. That's pretty fast, right? So we're going to find the angular speed in radians per second. So remember, to get the angular speed in radians per second, we just need to put our 9.3, that's in revolutions per second right now. So we'll need to times that by 2 pi radians, because every revolution, the angle changes by 2 pi per 1 revolution. So the revolutions will cancel. 9.3 times 2 pi, so that would be equal to 58.4. Remember, the revolutions canceled, we have radians per second. So once we have our angular speed in radians per time, in this case per seconds, now we can go ahead and find the linear speed by just multiplying it by the radius. So for part B, we're going to multiply 58.4 times 9 inches, okay? And remember, this was in radians per second, so usually we don't have to write the radians. It's just going to be, we're just going to be left with inches per second. So 58.4 times 9 is about 28.2, 28.3. I'm going to round it to 3. Sometimes that can change a little bit whether I rounded here or if I kept that as a longer decimal, but this would be 28.3 inches per second. Again, that is the unit that asked us to find it in, so we are good with our unit, so we can just leave it like that. Okay, so let's go ahead and try another one here. I'm going to hurry and erase that line that hung down. Okay, so the circular blade on a saw has a diameter of 7.25 inches. And again, that's the diameter, and we want the radius, so we're going to cut that in half. So 7.25 divided by 2, whoops, I'm just plugging it in really quickly, is 3.625. So this would be 3.625 inches. So that is the radius. It rotates at 4,800 revolutions per minute. So every minute that goes by, this thing goes all the way around 4,800 times. So to find the angular speed, we are going to take that 4,800 revolutions per 1 minute. We're going to change it to radians per second because that's what it's asking us to do here. So we're going to multiply this by 2 pi because for every 1 revolution it goes around 2 pi, right? That's a complete revolution. So the revolutions cancel here. And so first I'm just going to leave it as radians per minute. This is radians, right? And then we're going to have to convert that to seconds. So 4,800 times 2 pi, I think, let's see, 4,800 times 2 pi would be 30,159.4. So that'd be in radians per minute. Okay. But again, it's asking us here to do radians per second. So remember that there are 60 seconds in 1 minute. So those are equivalent. So because minutes is on the bottom here, in order to convert this to seconds, I want to put 1 minute on the top because I want the minutes to cancel. And I want to put 60 seconds on the bottom because I want this to be radians per second. So if I do it that way, the minutes cancel and I'm left with radians per second. Okay, so that's just, if this is on the bottom, it's just the same as this divided by 60. So 30,159.4, I'm going to hurry and put that in, divided by 60 is equal to 502.7 radians per second. Okay, so there's our angular speed. And now we need to take our angular speed, remember, and we're going to find our linear speed by multiplying it by the radius. Okay, we want our answer in feet per second. Our radius is given in inches, so we do have to think about that, but let's just go ahead and write this down. So our angular speed, I'm going to take that and multiply it by the radius, so 502.7 radians per second times 3.625, that's our radius, inches. So remember, we don't really have to worry about the radians being written down, so it's inches per second. And since we want this in feet per second, we're going to have to change this to feet. So remember, there are 12 inches in 1 foot. And because we have inches on the top here, we're going to put inches on the bottom. So 12 inches to 1 foot, that little fraction, we're gonna put it like that so that the inches cancel out with the inches, and I'm left with feet per second. So if I do 502.7 and I multiply that by 3.625, that gives me 1,822.3, if I'm rounding, feet per second. Okay, so that would be the linear speed of one of the saw teeth. Okay, so as it goes around the saw, that's how much ground it's covering every second. So it's pretty fast. Okay, a woman is riding a bicycle whose wheels are 30 inches in diameter. Again, it's giving us the diameter, right? So, and we need the radius. So we have 30 inches here is our radius. Nope, sorry, 15 inches. The diameter is 30, so the radius is 15 inches. If the wheels rotate at 150 revolutions per minute, so our angular speed is 150 revolutions per minute, find the speed at which it's traveling in miles per hour, at which she is traveling. So that's the linear speed. We're going to be looking for the linear speed, which is the angular speed times the radius. Okay. So we'll worry about the units in a moment. We're just going to work on making sure we get everything here. So the angular speed, remember, I need to change it. Before I can multiply it by the radius to get the linear speed, I need to multiply this by 2 pi radians over 1 revolution so that I can get it in the proper form here. radians per minute or radians per time to find linear speed. So if I multiply 150 times 2 times pi, that's going to give me 942.5 radians per minute. Okay. So now I'm going to take that 942.5, the angular speed, and I'm going to multiply it by the radius. I'm going to put minutes on the bottom here. I'm multiplying by 15 inches. But I want my final answer to be in miles per hour. So I'm not sure how many inches are in a mile, but I do know that there are 5,280 feet for 1 mile. And I also know that there are 12 inches in 1 foot. So I'm going to use these both. I'm going to first multiply this. I think of this as over 1 or whatever. I'm going to multiply it by, I want the inches to cancel, so I'm going to put 12 inches on the bottom, and that's equal to 1 foot, so I'll put 1 foot on the top. So that means the inches will cancel with the inches, and I'll be left with feet. And then to go from feet to miles, since feet is what I want to cancel out, I will put the 5,280 feet on the bottom, and I will put the 1 mile on the top. Then the feet will cancel and I'll be left with miles per minute. But again, I want miles per hour. So I know that there are 60 minutes per 1 hour. So I would also need to convert this per minute here. So because the minutes are on the bottom, I would want to put the 60 minutes on the top and the 1 hour on the bottom, so that the minutes cancel with the minutes and I'm left with hour. Okay, so now as we look across this, everything that's on the top will be multiplied together. Everything on the bottom, we're going to divide our answer by that. Okay, so if I take and I multiply 942.5 times 15 times 60 times 1 as well, but we don't need to actually do that, right? So 60 times 15 times 942.5, then take that answer and I'm going to divide it by 12 and also divide it by 5,280 feet. If I do all of that, it's going to come out to 13.4 miles per hour. Okay, so she's traveling about 13.4 miles per hour on her bike, which seems reasonable. So make sure that your answer seems reasonable for what it's asking. Okay, so on these next ones, go ahead and try them. Pay special attention to the units that they have. You may have to look up some conversions and things like that. But remember, whenever you're converting units, you want to make sure that the one you're trying to get rid of cancels out. So make sure it's on the opposite part of the fraction. And then the one that you want goes on the opposite to the one that cancels, right? So good luck with these guys. Try the homework problems. We'll talk about this some more on Monday, but have a great day.